Hello everyone, welcome to our channel. This is Zeb Bhatti. In this video we'll try to demystify a key technology component in the Metaverse experience stack, something we call extended reality or XR. So what does extended reality really mean? Extended reality is the technology that integrates the digital and the physical world to various degrees. It actually encompasses other concepts and technologies such as augmented reality, AR, mixed reality, MR, and virtual reality, VR. Mixed reality and the futuristic holograms like the digital objects shown in the Star Trek movies franchise allow human users to experience the metaverse through various alternated realities across both the physical and digital worlds. We'll begin with the well-recognized domain of VR first, and progressively discuss the emerging fields of AR and its advanced variants, MR and holographic technologies. This video will serve as an introduction to how XR bridges the virtual entities with the physical environments. First is virtual reality, or VR. The prominent feature of VR is the totally synthetic view. The commercial VR headsets provide usual way of user interaction techniques, including head tracking or tangible controllers. Users are situated in fully virtual environments and interact with virtual objects through user interaction techniques. VR is known as the farthest end from the reality in the reality-virtuality continuum. That is, the users with VR headsets have to pay full attention to the virtual environments and hence separate from the physical reality. The users in the metaverse will create contents in the form of digital twins. Nowadays, commercial virtual environments enable users to create content, for example, VR paintings. User interaction with virtual entities in a virtual environment, for instance, can allow modifying the shape of a virtual object and creating new artistic objects. Multiple users in such virtual environments can collaborate with each other in real time. This aligns with the well-defined requirements of virtual environments like a shared sense of space, a shared sense of presence, a shared sense of time, real-time interaction, a way to communicate by gesture, text, voice, etc., and a way to share information and manipulate objects. It is important to note that multiple users in a virtual world, that is a subset of the metaverse, should receive identical information as seen by other users. Users also can interact with each other in a consistent and a real-time manner. In other words, how the users should perceive the virtual objects and the multi-user collaboration in a virtual shared space would become the critical factors. Considering the ultimate stage of the metaverse, users situated in a virtual shared space should work simultaneously with any additions or interactions from the physical counterpart, such as AR and MR. The core of building the metaverse, through composing numerous virtual shared space, has to meld the simultaneous actions among all the objects, avatars representing their users and their interactions, for example, object avatars, object-object, and avatar-avatar. All the participating processes in virtual environments should synchronize and reflect the dynamic states events of the virtual spaces. However, managing and synchronizing the dynamic states and events at scale is a huge challenge, especially when we consider unlimited concurrent users collectively act on virtual objects and interact with each other without latency, where latency could negatively impact the user experiences. We'll talk about overcoming latency in a future video when we cover edge networks. Next is augmented reality, or AR. Going beyond the sole virtual environments, AR delivers alternated experiences to human users in their physical surroundings, which focuses on the enhancement of our physical world. User-generated computer content or virtual content can be presented through diversified perceptual information channels, such as audio, visuals, smell, and haptics. Haptics is the sense of touch mediated by technologies. Haptics identifies all the technologies that provide the sensation of digital touch feedback, also called haptic feedback. The first generation of AR system frameworks only consider visual enhancements, which aim to organize and display digital overlays superimposing on top of our physical surroundings. In the early 1990s, there was a bulky see-through display that did not consider user mobility, and it required users to interact with text and 2D interfaces with tangible controllers in a sedentary posture. But since then, significant improvements have been made to improve the user interaction with digital entities in AR. It is important to note that the digital entities from the metaverse, overlaid in front of the user's physical surroundings, should allow human users to meld the simultaneous actions. This is analog to VR. As such, guaranteeing seamless and lightweight user interaction with such digital entities in AR is one of the key challenges, bridging human users in the physical world with the metaverse. Freehand interaction techniques, as depicted in most science fiction films like Minority Report, illustrate intuitive and ready-to-use interfaces for AR user interactions. A well-known freehand interaction technique named Voodoo Dolls is a system solution in which users can employ two hands to choose and work on the virtual contents with pinch gestures. Homer is another type of user interaction solution that provides a ray-casting trajectory from a user's virtual hand, indicating the AR objects being selected and subsequently manipulated. AR will situate everywhere in our living environments, for instance, annotating directions in an unfamiliar place and pinpointing objects driven by the user contexts. As such, we can consider that the metaverse, via AR, will integrate with our urban environment, and digital entities will appear in plain and palpable ways on top of numerous physical objects in urban areas. In other words, users with AR work in the physical environments and simultaneously communicate with their virtual counterparts in the metaverse. This requires significant efforts in the technologies of detection and tracking to map the virtual contents displayed with the corresponding position in the real environment. The Turing machine was considered as the first research prototype that allowed users to experience AR outdoors. The prototype consisted of computational hardware and a GPS unit loaded on a backpack, plus a head-worn display that contained map navigation information. The user with Turing machine could interact with the AR map through a handheld touch-sensitive surface and a stylus. In contrast, the recent AR headsets have demonstrated remarkable improvements, especially in user mobility. Users with lightweight AR headsets can receive visual and audio feedback cues indicating AR objects, but other sensory dimensions such as smell and haptics are still neglected. AR headsets are not the only options to access the content from the metaverse. When we look at the current status of AR developments, AR overlays, and even digital entities from the metaverse can be delivered by various devices, including but not limited to AR headsets, handheld touchscreen devices, ceiling projectors and tabletops, Pico, wearable projectors, and so on. AR headsets have advantages over other approaches in terms of the switch of user attention and occupying users' hands. First, human users have to switch their attention between physical environments and digital content on other types of AR devices. In contrast, AR headsets enable AR overlays displayed in front of the user's sight. Secondly, the user's hands will not be occupied by the tangible devices as the computational units and displays are mounted on the user's heads. Such advantages enable users with AR headsets to seamlessly experience the metaverse through an AR lens. Now let's look at mixed reality, MR. After explaining the two extremes of the reality-virtuality continuum, AR and VR, we'll explain the relationship between the metaverse and MR. Unfortunately, there exists no commonly agreed definition for MR, but it is crucial to have a common term that describes the alternated reality situated between two extremes of AR and VR. Nevertheless, the vastly different definitions can be summarized into 6 working definitions, including 1. The traditional notion of MR in the middle space of the reality-virtuality continuum. 2. As a synonym for AR. 3. As a type of collaboration. 4. As a combination of AR and VR. 5. As an alignment of environments. 6. As a stronger version of AR. The above 6 definitions have commonly appeared in the literature related to MR, but the community views that MR stands between AR and VR and allows user interaction with the virtual entities in physical environments. MR objects, supported by a strong capability of environmental understandings or situational awareness, can work with other tangible objects in various physical environments. For instance, a physical screwdriver can turn digital entities of screws with slotted heads in MR, demonstrating an important feature of interoperability between digital and physical entities. In contrast, in the existing applications, AR usually simply displays information overlaid on the physical environments without considering such interoperability. Considering such an additional feature, MR is viewed as a stronger version of AR and is more connected and has more collaborating relationships among the physical, spatial, user interaction and virtual entities. So MR is the starting point for the metaverse, and certain properties of the 6 working definitions are commonly shared between the metaverse and MR. The metaverse begins with the digital twins that connect to the physical world. Human users subsequently start content creation in form of digital twins, etc. Accordingly, the digitally created content can be reflected in physical environments, while human users expect such digital objects to merge with our physical surroundings across space and time. Although we cannot accurately predict how the metaverse will eventually impact our physical surroundings, we see the existing MR prototypes encapsulate some specific goals, such as pursuing scenes of realism, bringing senses of presence, creating empathetic physical spatial. These goals can be viewed as an alignment with the metaverse, advocating that multiple virtual worlds work complementary with each other. Finally, we have holography large display projectors and pico projectors. Based on the existing literature, here we aim to make speculation for the ways of bringing the uniquely created content inside the virtual environments, ultimately the metaverse, back to the physical counterparts in the shared public space. As the social acceptability of mobile headsets in public spaces is still questionable, we lack evidence that mobile headsets will act as the sole channel for delivering metaverse content into the public space. Instead, other mature technologies, such as large displays and pico projectors, may serve as a channel to project pixels into our real world. Large displays and pico projectors allow users without mobile headsets to view digital entities with a high degree of realism. In addition, miniature projectors embedded inside smartphones, for example Movie Phone, allow content sharing anytime and anywhere. It is also worth noting that smartphones are the most ubiquitous devices nowadays, and they are getting better and better each year. Soon, most smartphones will be equipped with generative AI tools and features. Finally, we discuss the possibility of holographic technology emphasizing enriched communication media, exceeding the 3D displays and pursuing true volumetric displays, showing images or videos, that show no difference from our everyday objects. The current holographic technology can be classified into 2 primary types: reflection-based and laser-driven holograph. The main advantage of reflection-based holography is to generate the colorful holograms with color reproduction highly similar to real-life objects. On the other hand, plasma fairies is a 3D aerial hologram that can be sensed by the user's skin surfaces, though the devices can only produce plasmonic emission in a mid-air region no larger than 5 cubic centimeters. We conjecture that if technology breakthrough allows such volumetric 3D objects to appear in the real world ubiquitously, it will come as no surprise that the metaverse can merge with our living urban areas and provide a strong sense of presence to the stakeholders in urban areas. Holographic technology is fast overcoming its 3 key weaknesses: limited resolution, display size, and device mobility. Thus, overcoming such weaknesses may be the critical turning point of delivering enriched 3D images in the real world. Now, let's examine the challenges and the future of extended reality. As Metaverse moves from concept to reality, virtual reality, augmented reality, and mixed reality are a necessary intermediate stage. To a certain extent, virtual environments are the technical foundation of the metaverse. The metaverse is a shared virtual space that allows individuals to interact with each other in the digital environment. Users exist in such a space as concrete virtual images, just like living in a world parallel to the real world. Such immersive technologies will shape the new form of immersive internet, what many people now are calling Web 3. VR will allow users to obtain a more realistic and specific experience in the virtual networked world, making the virtual world operation more similar to the real world. Meanwhile, AR and MR can transform the physical world. As a result, the future of our physical world is more closely integrated with the metaverse. More design and technical considerations should address the scenarios when digital entities have moved from sole virtual, VR, to physical, MR environments. Ideally, MR and the metaverse advocate full integration of virtual entities with the physical world. Hence, super-realistic virtual entities merging with our physical surroundings will be presented everywhere and anytime through large displays, mobile headsets, or holography. Metaverse users with digital entities can interplay and interoperate with real-life objects. As such, XR serves as a window to enable users to access various technologies, for example, AI, computer vision, IoT sensors, and other focused technologies. In future videos on Metaverse, we will cover some of these other focused technologies necessary for the Metaverse to materialize. So please subscribe and stay tuned to our channel. We hope you enjoyed this video. Thanks for watching.